Hello, I'd like to take this time to talk about how do we deal with certain parts of the solid waste stream and what is the best alternatives based on economics of handling this material. So let me begin with this representation of the composition of the waste stream. The pie chart on the left is what most people think of in regards to waste composition. The pie chart on the right is looking at the same waste stream, but through a different lens. If we just look at packaging by weight, it is over 30% of the waste stream. If we just look at packaging, the pie chart here is the composition by weight. This pie chart is the same amount of material, but it is composition by volume. Now, weight is a consideration because it is the most accurate metric for assessing the amount of a material by using scales. And from that, you can charge a price for handling or disposal. Alternatively, volume drives design of storage capacity, processing capacity, size of equipment, and transportation capacity needed to effectively handle this material. Since packaging is such a significant component of the waste stream, while at the Tellus Institute, which is an environmental policy institute in Boston, my team decided to do a life cycle assessment of all packaging types, or what we call packaging materials, including all types of plastic packaging, both rigid and film, glass, metal, and all grades of paper packaging. Now, the ultimate purpose of why we were doing this life cycle assessment was to quantify the environmental impacts of choosing one packaging type over another. And once we quantified the impacts, then we would actually monetize those impacts or put a cost on those impacts so that possibly we could put a fee on the material on a per unit basis that would send an economic signal to the consumer of the particular packaging material to choose the least impactful packaging type. So we were going to create what we call an advanced production disposal impact fee that could be implemented by a state on materials that are manufactured within that area. So we would calculate the environmental impact cost by first quantifying the externalities and then monetizing those quantities. Then we would come up with a per unit tax or fee. Then we needed to choose at what level would this fee be imposed. Okay, and ultimately we made it at the point of production of the material as opposed to the production of a specific package type. That is, in order to track the fees and make sure that they are paid, as well as rewarding good behavior by changing or reducing the amount of harmful materials going into the packaging. It's much easier to do it at the manufacturing of the packing or packaging material. Now, this is just a quick representation of the life cycle. And we basically, this is the upstream supply chain from the point of extraction. That's how far up the supply chain did. But the impacts to be quantified were those after any pollution control technology already in place. Such pollution control technology required by regulations, in fact, internalizes the external cost of the impacts already, but not all of them. So this study was to assess the externalities beyond what current technologies were doing to protect human health and the environment. So let's get into how the LCA was developed. The first step was to quantifying the impacts. with any life cycle assessment, you have to determine what boundaries you're going to do as far as the analysis. And as I said, our upstream boundaries went all the way back to extraction. Our lateral boundaries basically was post best available control technologies. We also had to assess the quality of the data. And obviously in any analysis, there are assumptions made, and we list those assumptions clearly. And then we summarize the quantities of impacts for each of the steps through the process train. Now, these are all the materials we looked at. So the first set is basically the paper grades, and then we looked at aluminum for aluminum containers, steel for steel containers, glass, and then all the plastic grades, both for rigid containers and for film plastic. So that was the sum of our packaging material from extraction through production. And in framing the life cycle assessment boundaries, we also wanted to look at disposal, okay? And that is, what are the impacts, the comparative impacts from disposing the material versus producing the material. And again, we also wanted to look at, if we basically recycle the material, what the production cost of those recycled materials would be in comparison with the production of virgin material. So just focusing on the production side first, you can see that doing a life cycle assessment and the quantification of impacts and the associated monetization of those impacts of such a study can be quite expansive. But for this iteration of the life cycle assessment, we basically focused on the health impacts. This is because there was a good deal of high quality scientific literature about the health impacts of the materials that were going into producing the packaging. Correspondingly, the toxicology data in the literature was quite sparse regarding ecosystem impacts. So the boundaries of this was looking just at health impacts. So for any one material, this is, for example, generically for plastic material, there are multiple steps from raw extraction, natural gas processing, which is a processing of the materials that go into it, the petroleum refinery, again, more materials going into plastics, then from that, the organic chemicals productions, the polymerization that is creating the material, molding and forming the plastic, package filling, package purchase, product purchase and disposal. As you can see, these are all steps, and we basically had to understand each of these steps in order to understand what the inputs were and then what the outputs were post control technology. So, an example, natural gas processing. Okay, we would do a process flow diagram, and in that regards, this is an example of the one step in that natural gas processing, which is known as the aromatic production process step. For, in this case, was for PET plastics or PET plastics, the material that goes into Coca-Cola bottles, etc. And you can see there's multiple steps, processes that go into it, and multiple chemicals that are involved in that process. So as quantifying emissions, when we do a process flow for each of those steps, we want to understand what the raw materials and the energy going into the step. And then really we wanted to quantify post-treatment, that's post pollution control treatment, what the solid waste, the emissions for air, the releases to water, and other environmental releases that would be quantified so that we could eventually monetize it. So a conceptual pathway for impacts, as I said, you have a release of SO2. The stressor is SO2, the initial impact, maybe an acid rain, second impact on acidified lakes, tertiary impact on fish kill. Ideally, this would be the next steps in this study, but due to the limitation of time, budget, etc., we basically looked at toxic chemicals, greenhouse gases, air pollution, and really focused on health impacts. Now, to do this, we actually developed a procedure that hadn't really been developed before, and this is called Health Effects Ranking System, where basically we took all of EPA's list of hazardous materials that we had quantified coming out of all the steps in the extraction down to production of the materials, and we basically ranked them into classes. Now, the classes were carcinogens or non-carcinogens, and that was basically based on the literature. Is basically, what was the minimum amount of oral dose per day that would not cause harm, and that would be a baseline, and we can measure that in milligrams pollutant per kilogram of body weight per day. And then we were looking at toxicity itself, as basically as a toxic effects, and we had a long list of chemicals, but we knew that xylene has the highest dose to elicit a response. That is, it takes more xylene based on milligrams of pollutant to elicit a impact to human health. So we use that as a baseline. That was a scale, and thus we could rank every other chemical based on its milligrams of pollutant impact to xylene. So xylene was a reference dose, and so this is a relative scale, and then everything would be ranked against xylene as far as its impact, toxic impact. Now, for carcinogens, xylene is not necessarily a carcinogen, but there was also the impacts of carcinogenic materials. And so we had to combine both toxicity and carcinogenic materials. And so we did the same thing. We used isoflurone, used as the base, again, which what we call carcinogenic potency was judged. And again, isoflurone was the one dose, okay, based on milligrams of pollutant that on a daily basis by body weight that would cause or have a high probability of causing cancer. So we had all the chemicals for toxicity lined up against xylene, and all the chemicals for carcinogenic impacts lined up against isoflurone. And this was a relative scale of impact, okay, analysis. So this is what you see. We come up with a health effects ranking. And so we basically, these are concentrations in milligrams per kilogram of body weight. And so you can see they all have different numbers in this regards. And when you took the carcinogen and the non-carcinogen impacts, we had a combined ranking system. All the chemicals relative to each other as far as impacts to health. Once we had that hazard ranking, we also wanted to come up with a way to monetize cost. And so lead was on that list. And in the literature, lead is probably one of the most researched pollutant out there, primarily because it impacts on children. And there's good data on what it would cost to control lead. And it came down to $1,600 per pound. So we use that in that ranking system as the baseline, and based on the hazard ranking, we would actually use that to compare lead to things that are higher or lower on that hazard ranking page to come up with a lead price. Okay, and so that was for materials, and then for air pollutants, we actually used coefficients that came out of California studies on criteria air pollutant control. And for greenhouse gases, we used a Swedish study for greenhouse gas control, and then obviously energy costs associated with, through the life cycle analysis was compared to oil per barrel equivalent cost. So the monetization, okay, so we have the carcinogenic equivalents, we have the xylene equivalents, and we have this combined ranking, okay. And you see lead is not one, it's basically ranked as 1429 in the ranking system, but we know that that's $1,600 a pound treatment. So we, based on these numbers here, we can basically come up with relative cost based on health ranking. And so as we see here, lead was $1,600 a pound, and if we look at 2,3,7 tetrachlorodibenzene dioxin, which is one of the most toxic substances humans have created, you can see in comparison for the same amount of dose in milligrams that the pollutant price or health price is a factor of 1 million plus for this very toxic material. So by using, the health ranking system and then using the lead as our reference site, we basically could come up with, by quantifying all the chemicals coming out of all the processes for all the packaging types, coming up with cost. And so this is the summary of those costs. And so here are the plastic grades. These are the criteria air pollution cost. And remember, these are all post best available control technology for pollution control. So this is fugitive emissions, and this is what basically the cost of those fugitive emissions through the whole process chain of creating plastics, for example, or paper or the glass. You can also see that here's the toxic cost, okay, through the whole process chain for each of the materials, and here are the environmental production cost, okay, through those, okay. And when you add up this number here is the sum total of these two numbers here. These are basically what you see, and you see the big hitter here is obviously polyvinyl chloride, okay, and it's really a lot has to do with its carcinogenic and toxic impact because of the chemicals that go into creating this PVC, okay, in comparison. We also were looking at virgin versus recovered or recycled material, and there is a differential of bringing recycled material in versus virgin material, especially if you look at recycled aluminum, you can see that the toxic and carcinogenic impacts to recycled aluminum is much smaller than the impacts to using virgin material. The same thing here with criteria air pollutants. Okay, so you can see, for example, this material recycling of aluminum makes, from an environmental point of view, makes an amazing amount of sense. Okay. Now it's the production. Now what about the disposal side of the equation? Okay, so we basically would look at materials, we'd look at the waste stream being collected, going through processing, what percentage went through recycling, what percentage went to waste energy facilities, what percentage goes to landfilling, what percentage goes to composting, and then we would basically do the same thing as we did for production. We would look at post best control technology emissions, that's air, water, and any toxics that are coming out through through all the steps of the solid waste chain, including transportation of the material. Okay, and so if one looks at just disposal costs and the environmental impacts of conventional disposal, that is the sum total of the solid waste management system, which includes collection, possibly transfer station to disposal, and that's at landfill. This is basically the cost you get. And most of these costs are associated in this first column with the leachate that comes out of the landfill. Okay, and so if you can avoid that landfill cost by recovering material, it's great. And so this is basically if the material was recovered, if it is sent back to the recycling stream as an input on $1 per ton per day. So so for the material that would get recycled, okay, this is the impact. And so if you add the sort of conventional disposal impacts to the environmental impacts of the recycled material, this is the solid waste management system impacts over here on this last column. Okay. And so again, this is just looking at the disposal side of things. And so for the entire process flow of the life cycle analysis, there is both the production cost and the disposal cost. And even though this was not the point of the process, is that to look at the actual containers that were manufactured, we did do some analyses of that. We were more interested in the production of the materials that went into the manufacturing of the containers, not the containers themselves. But we did take our analysis down to the environmental cost, and this is cents per unit, okay? So that if you looked at, for example, you got half a gallon of juice in virgin glass material versus recycled glass, this would be the different environmental cost of those two, and then you could actually put those costs onto the product, and then people would make a consumer decision on whether it's worth it or not. Okay, but in that regards, making those decisions, do you buy the material in a PET container versus a glass container versus recycled glass container? Okay. Now you will see this is cents per unit, okay, and these units are in volume here. But even though if we go back and look at the impacts of plastics versus, let's say, recycled glass, plastics, the amount of plastic to hold the same amount of liquid is a lot less than the amount of recycled glass to hold possibly the same amount of liquid. So if you look at these three things here, okay, PET comes in the best from an environmental impact because it's lightweight, it has much less material. But going back to manufacturing, if we can capture the environmental impacts at the manufacturing state, then those people buying the material to create the products may change to a different material. So if we combine both the upstream and the downstream impacts, okay, of different products, okay, so the first one here is the conventional cost of disposal. Here's the environmental cost of recycling. Here's the environmental production cost, okay? And if you add those three up and then compare the numbers, you will say, yes, there is an environmental reason why we should be looking at very specific packaging types from an environmental impact and a monetization of those impacts. And again, this was post-pollution control. And recycling recovery, it shows that if you send more and more materials to recycling, okay, and back to production, then in that regard, you have a relatively small, very small production environmental cost versus virgin material production environmental cost. Because what's not not happening when you're using recycled materials. You're not getting all the emissions, post-control emissions from all these previous steps, okay, which were significant. And so you have just this one step of environmental impacts in comparison. And so it is a factor of a log 3, log 4 difference between the environmental impacts of recycled material versus the environmental impacts of virgin materials when you do the full life cycle assessment. So that's it. I hope this is informative, and I'll talk to you soon.